Hi, everyone. Yes, thank you for saying the title of my talk because that was going to be the first thing that I was going to say. Um, so the question that really informs all of this work that I'm doing right now is what can emerge from collaborations between science and music and scientists and musicians. Um, I'm based in the UK, and my name's Suzie, and I'm a trained Western art or Western classical musician. So all of my lens comes from that view. I play the oboe professionally, and also, as you can see here, my piano. And I actually got a message from Bob just then saying, was I ready? And I was actually just playing along with that song that was going on, so I completely missed his message for a bit. So this informs my work. And I use my voice all the time, although as an instrumentalist, I also want to broaden the definition of voice to include musical instruments. And my focus at the moment is particle physics and quantum physics in my work. And what this work has led me to the conclusion is that particle detectors and particle accelerators are actually a form of musical instrument. So if you think of like a drum, which has material stretched over the top, it's called a membranophone. I kind of think of these detectors or accelerators rather clunkily as particellophones or atomophones. This is the name I've given them. And my work is all about collaboration with physicists at the moment. And it's also about collaboration between the scientific process and specifically the findings of this process with reference to astronomy, particle and quantum physics. And I'm going to focus on the subatomic realm today and proton and making proton into music and how we do that. So I'm interested in how these ideas are already music and how do they structure the music that we can make. I work a lot with particle physicists and they provide me not only with a wealth of information, and they educate and teach me as well with enormous generosity and patience. So thank you to them. I'm interested also in what emerges from a creative collaboration, what we express from a place of relationship. So the relationship is not just between the physics and the music, but it's also between the people who are working in these realms. And what happens when we get scientists and musicians together? What can happen? What will we make? So it's a spirit of inquiry in my work. And actually my next project, it's very early days that I'm constructing, is to take these personal relationships I have with physicists and extend that to teachers of music and teachers of science and then students of music and science, and to bring these students and teachers, composers and scientists together to create music. So anyone who's interested in making that project with me or being involved, I'd love to hear from you. My email address is on my presenter page. So the physicists I work with at the moment are George Redlinger of Brookhaven National Laboratory, Mateus Carneiro of Brookhaven National Laboratory, and although they work at the same laboratory, they're not involved in the same kind of field. Elena Gramellini of Fermilab. And I actually made a film with Elena about neutrinos. She's a neutrino physicist. And that's also going to be on my presenter page. But the way we collaborated was really interesting because she had a very clear vision of the music she wanted. And so it was more like I was composing the music that she was wanting rather than I was saying, oh, this is the music that's needed here. So it was a very close collaboration in that sense. And I actually feel like she's the composer of that music. We talk about that a lot. Yasmin Emis at CERN and Steve Goldfarb at CERN, and also Tim Morris of Southampton University. And although these people aren't here in the conference, they're very much here in my work. They inform and help so much of what we do. And I see them as collaborative composers. And all our interactions take place online. And in 2022, I'll be the composer in residence at Fermilab. And that will be an online residency. And it feels important to say that because this is a virtual conference and we're all online, and I'm speaking from the UK and we're all dotted all over the world. And I think the online sphere gives us a way to, I don't know, be more diverse actually, and to have a richer, such richer, more, I don't know, interesting experiences. So a lot of my work is informed by the question I have about what music is, like why is music music and not something else? I think about it a lot. And the definition I currently work with, which again is coming through my lens of Western classical music, is in order for something to be music, it must be durational or have duration. It must be vibrational or have vibration. There's some kind of organizing principle. There's an organizing principle, or something is organizing it. And there's also a context. So for much music, it's emerging from a social context. But I think in terms of particle physics, we can think of the fields and the masses of the particles and the way those things interact also as a context. So for me, in this sense, the universe is a piece of music which is continually composing itself, that we're in the middle of all the time. And this is where improvised music comes in, because I think non-idiomatic improvisation gives us a way as beings, as human beings, to really dig into that idea of the universe continually composing itself, and to connect to that and then start to make music from that. But from here, we can also understand that particle physics interactions are also music, and we can start to translate them directly over into this music structure in the cultural sense of the word, and experience these unseen ideas. And somebody spoke about this earlier in the conference, I can't remember who, so I'm sorry, but this idea that these things are unseen or unknown, and we can actually, if we view the particle physics realm in this way, we can bring these ideas into an embodied space of vibration that our bodies and our beings can experience. And that really excites me. That's what this work is about. But we also find particle physics provides us with novel harmonic, scalic and rhythmic structures and patterns, as well as new narrative and formulaic possibilities. And this is really exciting to me as a composer. So this is what I mean when I talk about music of the atoms. And as a composer, I see myself as someone who is sort of finding a way to try and express this or translate this rather than impress something. So I'm going to dive in now and talk about how I'm starting to work with the proton, the system of the proton. And this is very much a snapshot, not only of my understanding of the proton, and so all of the wonderful physicists I spoke of before, any misunderstandings I have are my fault and not theirs. They do such a good job of supporting my understanding. But this is like a snapshot, not only of my understanding, but also of a creative process. So I'm going to translate or talk us through the translation of the pitches for the quarks that are in a proton. So the proton has familiar valence quarks, and quarks are fundamental particles that make up matter, I should say that. And there are 6 different types of quark. And the matter that makes up everything that's around us right now, or everything, is mostly made up of the first generation of quarks, the up quark and the down quark, the valence quarks. The proton also has Cquarks in, which involve more generations of quarks. So we have the up, down, and the strange and charm quarks. That goes into the 2nd generation of matter. And these Cquarks, and it's C in the sense of the huge body of water, they're continually popping out in and out of existence. They're like virtual particles. They pop out, you have a particle and an antiparticle pair, then they annihilate each other and poof, disappeared. And they contribute less energy than the valence quarks to the proton, but they still contribute enough energy. And this is like structure function. This is called the structure function of the proton, and you can read a lot about that, as I'm doing right now. So what happens is when we take these pictures, we translate them over into like a scale system that we can then start to compose with. And we can do this in one of 2 ways. We can just take the pictures and use that as a system to compose with, or we can take the pictures and do what I'm more interested in, which is to start to use the system of how these things interact to design the music. That's what I'm more interested in. And I'm focusing on the proton because it's the first part of a piece I'm making with Mateus Carneiro, who I mentioned earlier, where we're creating the music of the acceleration process of how we make a neutrino beam, which starts with a proton. It actually starts with a little hydrogen bottle, and they open the hydrogen bottle and then get the protons that way, which just tickles me so much. And somewhere on the Fermilab website, there's a video of somebody bringing in a proton bottle. And this is actually how this entire piece will begin, with the proton bottle. So I'm going to start with the valence quarks and come to the piano now. And I hope you can, there we go, see, here's my lovely piano. So as I mentioned, there are 2 up quarks and there's 1 down quark. And all I did was very simply, I took the energies or the masses for each quark and I turned it into a figure that could be easily translated into hertz. And then from there, of course, a note. So the up quark has 2.3 mega electron volts of mass or energy, and that becomes 230 hertz. And in scientific pitch notation, that's a note we call A sharp 3, which is this note I hope you can hear. And actually the quark is ever so slightly flatter than that. But this is something that we're going to figure out with tuning. So what particle physics gives us is a whole new tuning system, which is so exciting to me because this piano is based on a very particular tuning system, which was invented in the 18th century. We think Bach actually invented it, or it's anecdotally said that Bach invented it. So the quark is slightly lower than that, and we'll sort that out later in another talk that I will do as well. I'll talk about that. Then the down quark, which is 4.8 mega electron volts, becomes 480 hertz, which again in scientific pitch notation becomes a note called B4. And if we listen to the two together, we get this interval called the minor ninth, which is not everybody's favorite interval, but nonetheless, here it is. And it's deeply fruity, it's a bit clashy, it's very resonant, it's very exciting for me as a composer. And Beethoven loved to use it. It has full of tension that we want to resolve. So what happens when we translate the particle masses, though, is something quite interesting, which is the heavier particles become the higher note, because, of course, the heavier something is, the higher the number that's associated with it. So in this case, 4.8 electron volts, which becomes 408 hertz. So we get our higher note, and the lighter particle becomes the lower note. And this feels to me very counterintuitive. And I think, because if I'm listening to lower sounds, I think of heavier things and I think of slower things. So what I've decided to do is I've switched them. But what the important gold, if you like, from this is the interval distance between the two. This is the relative distances between the mass ranges of the particles. That's the story that we can really keep. So what I do is I keep them in the same place in the piano, and I just switch them over so that now our up quark becomes A sharp 4, and our down quark becomes the minor ninth away, which is A3. And I want to keep it roughly in the same place on the keyboard as well, because this is a really nice place for us as human beings to vibrationally engage with. Too high and it's going to be just too much. And actually something me and Mateus often joke about is a lot of particle physics is like audible to dogs but not to human beings. So we want to keep it in a place that we can actually engage with it. Too low and it becomes something else. So we want to keep it there. That's a really nice place for us. Now the Cquarks I've derived differently, as I've mentioned, because they are their own system. Not only do we have an enormous mass range of difference, so we've got the up, down, strange and charm quark, and the distance is enormous. We have electron volt with the up quark, and the strange quark, charm quark, sorry, is 1.275 giga electron volts. So there's a massive range difference. It wouldn't fit on the piano if we use the same system, or on, the instruments or voices that we're going to use in the piece. So I squish them using a log 10, or narrow them so that they can be translated over into the embodied space of music that we can appreciate. But also I want to derive them differently because they operate differently within the system of the proton. So they're a contained system themselves. So what happens is the up quark becomes A sharp 3, the down quark becomes C4, the strange quark becomes G4, and the charm quark becomes C5. And again, we have the same problem with the heaviest particle, the charm quark, becoming the highest note, and the lightest particle becoming the lowest note. So I've just switched them over. So here they are. Here is our up, down, strange, and charm. And here they are with the valence quarks. And I don't know if you can hear it, but that fruity little clash, or you may not experience it this way actually, suddenly changes into not being quite so disturbing anymore. There's a different kind of harmonic thing that happens. Now remember that none of these things are exactly in tune with my piano, so there's going to be something more interesting that's going to emerge when we start to tune these together. And of course, because of the Pauli exclusion principle, which quarks are subject to, they can't exist in exactly the same quantum state, so they're kind of all jostling around this state as well, so we can really do that with the tuning, which is something I'm really excited to explore. So we also have antiquarks, because when the Cquarks are kind of popping out, a quark is produced, but we have to have an antiquark pair because we have to have a zero energy has to be maintained. So a quark pops out and an antiquark, and then they annihilate each other and things return back to zero energy again. And this can happen with gluons as well, but we haven't got to gluons yet. That's another entirely other question. And what we can do is we can describe the antiquarks actually using the pitches we've got, but within the way that we make those pitches interact within the piece of music. But something I think is quite interesting is we could exploit the cycle of fifths. So this is a system that we have in classical music that orders all the keys. It orders everything. And the anti-chord, if you like, is the one that's exactly halfway away, or the opposite. We could use that, which is the interval called a diminished fifth. So we could have these pitches and then the diminished fifth away, and that could become our anti-quark. And that's quite an interesting idea for me. I don't think it's actually going to fit with the physics, but as a composer, it was an interesting thing. And when we put the valence quarks, the Cquarks and the anti-quarks of the Cquarks together, you get a really interesting, really rich scale. And we could just take that and compose with that. We could say, oh, we've derived this from the proton, and we could put it into this system and we could compose with it. And that would be a wonderful way to work. But I want to go a bit further than that with this work. So the next step is to put these things into the way the proton system is actually operating, and to include the gluons and how they would impact on the system. Now, one thing about the Cquarks is they are giving less momentum. They move, I don't think movement's the right word, but they have less momentum in the system. They are slower, they have less energy. And something I thought about was to put them lower down on the piano. So you'd have your valence quarks here, and you'd have your Cquarks down the bottom. Keeping them contained in the center is nice, because it's like the proton. The proton is like this very, very contained system, which is operating at very, very small scales, which is defined by the strong nuclear force. And the gluons are the particle that mediates the strong nuclear force. So they're like the particles of the strong nuclear force. So there's something nice about having it all contained, but I also like the idea of putting the Cquarks down here, having the valence quarks here. Also, they're a bit more obvious, right? They're providing more energy. But having them down low in the range of the sounds that we're going to use gives us this sense that they have less momentum, they're moving more slowly, they're providing less energy. So I'm going to finish. I'm really looking forward to any questions. I'm just going to finish by playing the proton system to the piano, and then of course we would take these pitches as a starting point, as a jumping off point into telling this further story of how the proton is. So I'm going to finish by just playing these to give you a chance to hear them, and then I'd love to hear any questions if there's time.
Thank you, Suzie. So one question that's come in. So by tuning, I assume that you're talking about equal temperament. Is that right?
That's correct, yes.
Okay. So so is it obvious that the pitches that would be needed would just really correspond pretty close to the pitches on a piano as is, and not need to be generated by a computer to get in between notes? Or what about something microtonal by divide? Would it be a better fit to divide the octave into more than 12 parts, like 53 has been used a lot?
Yeah, yeah, absolutely. And that's something that I'm really thinking about, is how we would maybe need to retune our instruments. And one of the things I want to also do is bring in performers. So in the proton system, we might have, say, 8 performers playing a quark, because there are 8 different gluon systems that it can be interacting with. And that gives us 8 different colors, or 8 different tonal colors. And the idea would be to invite them to bring in us as human beings. So rather than worrying about tuning things exactly, to sort of have them tuning around roughly 230 hertz, for instance. And we might say to a musician, that's close to A sharp 3. That would be certainly helpful to me, but it wouldn't be helpful to everyone. There would be other ways to kind of do that, and then have them jostling around. But yes, certainly I'd be thinking about different tuning systems. And the American composer Lamont Young completely retuned the piano using unbelievably complex math. I mean, I don't understand it. And another person actually worked it out with a computer, with a calculator, pen and pencil, and annoyed Lamont Young very much. He was not fond of that. Anyway, so in answer, yes, absolutely.
And what settings have you, or would you share this kind of work? Is this something of interest to just other, music scholars, or could you see this being used for general audiences, or in a classroom setting?
I think it for all. I think this is like very much the early stages of developing this work. But when I'm doing my Fermilab residency, I want to do this piece as like my final piece in my final concert that I do. So this is very much to be shared with the general public, with students, that's the whole point. Absolutely.
And a question just came in. Early in your talk, you mentioned that there were rhythmic structures as well as pitch structures associated with particle physics. Could you elaborate on that a little bit?
Absolutely. So I think when, the music I'm trained in, classical music, time is divided up in very particular ways. And it isn't really until the 20th century that those ways get challenged, I think, or that new novel ways begin to open up. We have crotchets and minims, and everything's divided by 2 or 3, sometimes 5, and that tends to freak most classical musicians out if they see a 5. And everything's kind of tends to be coordinated around a rhythmic, even space. But particles don't do that. So there's lots of chance. It's probabilistically determined, it's statistically determined. So for instance, when something is going to happen, we don't know when it's going to happen, but we know it is going to happen. So later on in this piece, for instance, in the neutrino beam production, this proton has been turned into pions and kaons. So these are mesons, these are like 2 quark pair particles. And then they're left in a decay pipe to decay. And the decay pipe is measured out to be the distance that these particles need to be in the decay pipe for the amount of time that they will then decay into being muons and neutrinos. Now, pions and kaons will decay in very particular ways, and we know what those ways are, or at least we know of some of the ways that they do it. Maybe there are other ways that we don't know of right now. So we can score those out using this kind of system. These are pieces of music. And I think I would encourage you to all look at Feynman diagrams of particle physics, because they do look like little scores. I mean, they are, I know they're mathematical, but they're little scores. So we can use those then. And then what we do is we give that to the musicians and we say, look, to start off with the pion and the kaon, that's going to be a chord system. in my imagination. It's some kind of chord system, although it'll probably be much more complex than that. And then there's going to be a duration of time set by the decay pipe. Now, in traditional classical music or anything else, we don't really think about times. Like John Cage, when he wrote 4 minutes 33, he was defining the time frame, but we tend not to do that. We're just like, well, the music lasts for this long, and that's how long it lasts. So the material is defining the time frame. But here, actually, the time frame is very clearly defined by the decay pipe. But we can't say to the musicians, you have to play this bit then. All we can do is say to them, by the time it gets to this point, you've got to have done this a certain quantity of times, and then have muons and neutrinos, and this is what the muon and neutrino material is. So this is what I mean about the rhythmic. It's a different kind of way of thinking about time, and new rhythmic possibilities emerge, and new narrative and time frame based possibilities emerge. That's what I'm getting at. And we have to use chants a lot more.
So 2 more questions have come in, but I think we just have time for one of them. So I'll read you both of them and you can choose which one you want to answer. So one of them says, could we transcode leptons, bosons, fermions, etc. as time signatures, types of notes, speed, and compose, say, the orchestra of matter? And the other question is, if you were to play this music by an orchestra, how would you decide what to assign to each instrument?
I think the first question, I say yes, of course. In my work, I'm really interested in like the direct translation across. But yeah, yes, absolutely. And I will answer both actually. And although I can't remember what the second one was because I got so excited.
How you would assign to different instruments?
Oh, that's an interesting question. Yeah, I think that has to be about pitch. That has to be decided by the particles and what the instruments are. So for instance, like the ranges of an instrument that's possible. Okay. So something might be out of range of one instrument and they couldn't play it, but actually I'm less interested in which instrument does what. And that might actually be up to performers to decide that in the moment.
Right, because you were talking about moving things to a convenient octave, so the range wouldn't be the issue, but timbre might be the bigger issue. You know.
Exactly. And the thing with, just to go to the proton, is the the valence quarks are continually interacting with gluons, and that's actually changing the color of them. And that's a whole other thing, color charge and flavor charge and all these kinds of things that are going on. And how we can work with that is actually to express that through changing timbres. So that's actually a thing that's really, really important. And then that has to be done with different instruments. And again, composers don't decide that. The performers have to decide that in the moment. Right. The composer, just me in this case, just says this. It's sort of like I have to give them the instructions to do that, but we have to figure out in the moment when to do that. So there's the improvisation part comes in, that picking up. Yeah.
Well, thank you so much for a fascinating talk. I look forward to all of us talking more about everything at the networking sessions. We have a short edutainment break before our next, before Tracy Palmer speaks to us from Australia. Thanks again, Suzie.